Okay, so we're going to be looking at how to find limits that are of the indeterminate form. We're going to be using algebraic and Lhopitals rule. Now, before we get started, we're going to take a look at what indeterminate form means. So recall, there are two forms you want to keep in mind. There's the indeterminate form, indeterminate. The indeterminate form comes in multiple forms, but the only one we're going to be focusing on in this course is 0 over 0. Okay? Indeterminate form is easily confused with the undefined form. So undefined form is a number divided by 0, where the number is not 0. Okay, so if you have a non-zero number divided by 0, that is known as undefined. In that case, the limit does not exist. If you have indeterminate form, then we can use either algebraic manipulation or Lhopitals rule to evaluate the limit. Okay, so these two forms you want to keep in mind. Now let's try out the following question. Let's go ahead and consider the following question. Let's say you're to evaluate the limit for question 1. Let's say you're asked to compute the limit as h approaches 0 of the square root of 2 plus h minus the square root of 2. This entire expression divided by h. Okay, so since this is a finite limit, we're going to substitute first. Okay, that's your first line of attack for finite limits. So substitute first. So if I substitute, I'm simply going to plug in h into 0 into h for this expression here. So we're going to have the square root of 2 plus 0 minus the square root of 2 divided by 0. And then if you simplify this, you have the square root of 2 minus the square root of 2 over 0, which is equal to 0 over 0. So this answer is known as an indeterminate result. Indeterminate. Basically, we do not know what the limit is yet. Okay, so anytime you have an indeterminate form, you can the problem is not over. You have two options. You can either use Lhopitals rule or algebraic manipulation. We're going to take a look at both methods and see which one is more effective. So let's use the algebraic manipulation first. So algebraic manipulation. Okay, so we're just going to use the tools of algebra to see if we can manipulate the answer into a form where we do not get an indeterminate form when we evaluate the limit. Okay, so the original problem was limit as h approaches 0, square root of 2 plus h minus the square root of 2 divided by h. Now, different tools you can use factorization, expansion, you can use rationalization, you can use identities. Whatever form alters the algebraic expression you have, changes it into another form, that is what you're going to use. Anytime you have radical components, the approach is rationalization. Okay? In this case, we are going to be rationalizing the numerator. So to rationalize the numerator, we're going to be multiplying by the conjugate of the numerator, which is root 2 plus h. You have a minus here, so you invert the sign, plus root 2. You multiply the numerator and the denominator by the conjugate of the numerator, which is a radical expression. We're going to use a shortcut here, so you have to remember this rule for algebraic consolidation or expansion. So you just want to remember that if you have a plus b times a minus b, this is the expanded form of a difference of squares, a square minus b square. Okay, so if we take a look at what we have here, we have a root 2 plus h minus b, and then we have a root 2 plus h plus b, a minus b times a plus b. So using this formula right here, we can condense this numerator expression. This can become the limit as h approaches 0 of a square plus b square, which is the square root of 2 plus h quantity square minus the square root of 2 quantity square. That entire thing divided by the denominator, which is h times the square root of 2 plus h plus the square root of 2, like that. Now we're going to simplify the numerator. This is going to become the limit as h approaches 0. You have the composition of two inverse functions here. Square and square root are inverses, so they take each other out. And then you have 2 plus h minus, the same applies here. You're squaring the square root of 2. So these two take each other out. And then you have 2. And this entire expression here divided by the denominator, don't distribute the denominator. Just leave h out. So let's continue writing down the denominator. It's the square root of 2 plus h plus 2. Okay. Now if you examine the numerator, what you notice is that the 2's cancel out since they're opposites. And then you're left with the limit as h approaches 0 of h divided by h times the square root of 2 plus h plus 2. Now, these two h's divide out, and you're left with, this becomes the limit as h approaches 0 of 1 divided by the square root of 2 plus h plus, I left out the root 2 here, plus root 2, like that. Okay. Now, let's see, we're going to plug in 0. Again, because we've simplified it completely, if we plug in 0, we're going to have the, let's plug in 0. This is going to become 1 over the square root of 2 plus 0 plus the square root of 2, which becomes 1 over root 2 plus root 2. Your final answer is going to become 1 over 2 root 2. Okay? If you rationalize the denominator by multiplying top and bottom by root 2, this can also be written as root 2 divided by 4. Alright, so let's try the same problem using Lhopitals Rule. So we've seen the algebraic manipulation approach. So now we're going to use Lhopitals Rule. Okay, so for Lhopitals Rule, since we have the indeterminate form, this is how you approach it. The limit of this simply becomes the same thing as the limit of the numerator, the derivative of the numerator and the denominator. Okay, so Lhopitals Rule says that if you have the limit of a quotient, that limit is the same thing as the limit of the derivative of the top and the derivative of the bottom. So using Lhopitals Rule, we'll just differentiate the top and the bottom separately, okay? So you have to differentiate them separately. So all we're going to have to do here is differentiate these three terms, plug in 0, and see what happens. The only complex component of this problem is differentiating the square root of 2 plus h, which is a composite function. So let's pull that out. Root 2 plus h. I'm going to call the outer function f. F of h is 2 plus 8 is root h. And then the inner function is g of h, which is 2 plus h. Now using the chain rule, we're just going to differentiate the outer evaluated at the inner times the derivative of the inner. F prime is 1 over 2 root h, and g prime, the derivative of 2 is 0, the derivative of h is 1. Alright, so to proceed, we're going to have the derivative of the outer evaluated at the inner, so plug this in here, and then we're going to be multiplying that by the derivative of the inner, which is 1. Okay? So the derivative y prime is going to be 1 over 2 root 2 plus h. Okay? Now let's go back to the problem. The problem asks we had to find three derivatives. Okay? So the problem is now going to become the limit as h approaches 0. The derivative of root 2 plus h is 1 over 2 root 2 plus h based on the work we just did. The derivative of root 2 is 0, and the derivative of h is 1, so over 1. So that gives us the limit as h approaches 0 of 1 over 2 root 2 plus h. Because when you subtract 0, that's the additive identity, you have the same thing. When you divide by 1, you end up with the same thing again, and then that's what you have. Now you plug in 0 into this expression, and you end up with 1 over 2 root 2. Okay? And I think that's what we got over here, 1 over 2 root 2. Or if you rationalize, it's the same thing as root 2 divided by 4. That's when you multiply this by root 2, top and bottom, you have root 2 over 2 times 2, which is 4. Okay, so there goes the two ways that you can attack a problem if it's in the indeterminate form.